before we do the recursive functions and recursion in general, let's do a review of piecewise functions. So do you remember in college algebra, you learned about something called piecewise functions? So these are when you put a little bit of logic into a function instead of just like x plus 2 or something like that. So if I say I have a function f of x is equal to 3, if x is less than or equal to 5, and it's equal to 10 if x is greater than 5. Somebody try to tell me what the value of, now this is going to be sort of like a workshop. I'm going to ask some of you questions today. So somebody tell me what the value of f of 1 is. What's the value of f of 1? 3, right. Now somebody else tell me the value of f of 2. Correct. Somebody else tell me the value of f of 3. It's getting harder as time goes by. So if everybody says 3 and then you keep saying 3, it could turn out to be something different next time though. So what is f of 3? Anybody know?
3.
Yep. Okay, what's f of 4? What's f of 5? Okay, now I need somebody new to tell me though this time. What's f of 6? Okay, that's what I thought you might say, but that's not actually right. It's not 3. It's 10. But why is that? Because the x value that you're plugging in is greater than 5, and so if the function if the x is greater than 5, the function equals 10. You see that? So you have to read the instructions. Just like everything in this class is basically just reading instructions and knowing when things suddenly change. Let's do another piecewise function. So f of x equals to 1 if x equals 0. It equals f of x minus 1 if x is greater than 0. So tell me what f of, actually, in fact, I'm going to change it to say less than or equal to 0, like that. So tell me what f of 0 is. What's f of 0? Correct? Okay, hold on, let me check the type. Okay. 1, yes, correct. Okay, what's f of 1? So this is what they call a recursive function. So f of x, if x is bigger than 0, is 1 bigger than 0? It is, right? Then f of 1 equals f of x minus 1. So f of 1 equals f of x minus 1, but what value am I plugging in for x? So no, I'm plugging in 1. So you get 1 minus 1, which is what? So you get f of 0. But what is f of 0 though? Right. So this is what's called a recursive function. And recursion in computer programming and in discrete math is one of the only ways to do certain tasks. Like if you want to break down an image or something like that into like various components, the only way to do it is by breaking it down one piece at a time and then breaking that down at a higher level and then breaking that down at a higher level. In fact, exponential growth and everything, in fact, cellular division and things like that, all kinds of things are based on kind of like recursion. Something happens, and then within that process, something else happens within that process, and then something else happens within that. So what's f of 2? Well, yes, that's correct. But first of all, what is f of 2 though if I plug it into the function though? F of 2 is f of x minus 1, which is f of 1. And f of 1 is f of 0. What is f of 0? 1. Right. So now let's do something slightly more complicated though. Let's look inside the book real quick. And By the way, you have to be reading the book in order to understand this class. So make sure you're always reading the whole chapters over and over and over and over and over and over. Okay, let's go back to something really cool. All right, so look at the bottom of page 380. And this tells you Ackermann's function. By the way, has anybody ever met somebody whose last name is Ackermann? There used to be a well-known psychologist at Wichita State named Paul Ackermann. Ackermann's function. Sorry, I left off the S. Ackermann's function. I don't think this was the same Ackermann, though, but it could have been, though, because some people know about everything from psychology to math and everything, but okay, so this function was named after Wilhelm Ackermann. Okay, it's not the same Ackermann, but he was a student of the great mathematician David Hilbert. So it has a value of m and a value of n. And this is a piecewise function. So it equals 2 times the value of n anytime the first number is 0. So if the first input value is 0, you'll get double the second input value. So does everybody understand the first piece of it? This one's not the complicated part. The rest of it's what's complicated. It always equals 0 anytime the m is greater than or equal to 1 and n is 0. So if the if the second input is 0 and if m is bigger than or equal to 1, then it equals 0. So does that make sense? So basically, if n is 0 and m is bigger than or equal to 1, then the output value is 0. There's a couple other pieces, but let's practice with the first two pieces, though. Somebody tell me what a of 0, 3 is. What is a of 0, 3? So which number is m? Which number is the letter m, like M&Ms? 0. So which of those two pieces should apply to the input 0 and 3? Should the top piece or the second piece apply? Top piece, right? So that means that we have to plug 0, 3 into the top piece because it says if m is the first number, which is 0. If m equals 0, the answer equals 2 times the second number, right? Second number is called n. So what's the output value for a of 0, 3? It's 2 times the second number, which is 6. Correct. Okay, let's try another test example of this Ackermann's function. So let's make m be greater than or equal to 1. Let's just say 5 and make n be 0. So it's a of 5, 0. 0, correct, because the second piece applies to that one. Now let me add you the two final pieces to this. The Ackermann function equals 2, just the number 2 with no n or anything in it, just 2 itself, if m is greater than or equal to 1, and if n equals 1. Then the last piece is the recursive piece. So I'm going to practice with the third piece first. So what is a of 7, 1? What's a of 7, 1? 2, correct. Now let me put in the last piece. The Ackermann function is equal to the Ackermann function, again, of m minus 1, comma, this has double recursion, a of m, comma, n minus 1, if m is greater than or equal to 1 and n is greater than or equal to 2, like that. So let's do that piece. So give me a value, what's the first value that's greater than or equal to 1? What's the first number that's greater than or equal to 1? 1, right? So let's plug in that value for m. And what's the first number that's greater than or equal to 2? So let's plug that number in for n. So what's a of 1, 2? Let's read through this carefully. Everybody needs to understand this. Hey, don't be looking down at your page or anything like that. Make sure you're watching. Okay. So what's a of 1, 2? What's the Ackermann function of n minus 1 of a and n minus 1? First of all, what's m? 1. But what's n? 2. So what's m minus 1? Correct. So that equals a of 0. Now let's read the next part. It equals a of n minus 1, which is a of 0, comma. Put the comma down. And then a again of m. What's m? What's the original value of m that I'm plugging in? 1. Correct. And then n minus 1. What's the value of n by itself? 2. So what's 2 minus 1? 1. So it equals a of 1, 1. Boom, like that. So a of 1, 2 equals a of 0, comma, a of 1, 1. So do we know what a of 1, 1 is, though? No, we don't. So we have to go figure that out first. So what a recursive function does is it reduces the input value of a large number or a large input into some other value of a lower level input. So a of 1, 1 would equal, which of those 4 cases would apply to a of 1, 1? It's not going to be the last case. It's going to be one of the other 3. Third one. So what is, and remember the third one says if m is greater than or equal to 1, which it is, and n equals 1, which it is, what does the Ackermann function equal? 2. So a of 1, 1 equals 2, right? So the a of 0, a of 1, 1 breaks down into a of 0, 2, because a of 1, 1 is equal to 2. And now that you have a of 0, 2, what is a of 0, 2? Which of those cases applies to that? This case says if m is 0, is m equal to 0 in that case? Yes. It equals 2 times the second number. So a of 0, 2 is equal to 2 times the second number. 2 times 2, which equals 4. So a of 1, 2 equals 4. Do you understand how it works? Now it does get a little bit complicated though, because if you did a bigger number than a of 1, 2, you'd probably have to actually end up a of 0, 1, and then a of 1, 1, and then you'd actually end. So let's say since it ended up being a of 1 and a of 1, 2, then you'd actually break the a of 1, 2 again into a of something smaller. So you just have to keep breaking it down into smaller and smaller pieces. A lot of the games that you actually play sometimes are actually somewhat recursive because you have to like do something, then do it again until everything stops. Can anybody think of anything else recursive in math that possibly could, and by the way, almost everything could be recursive, even adding could be recursive. Like n plus 1, you could say is equal to f of n plus 1, for example. Can anybody think of do you know what this number means? N factorial. What does n factorial equal? N times n minus 1 times n minus 2 times what? How far does it go? To get, no, not 0, because they need to get to 1, right? So n factorial is like that. Is there any way to define n factorial recursively? Yeah. So f of n equals n factorial. Is there any way to define that? Because what if somebody didn't know what that meant? Because by the way, the exclamation point has no definition until somebody has defined it. How could you define what the exclamation point means without using an exclamation point? Because you're just using circular reasoning if you define something without ever using some other definition for it. Like if I said, what does green mean? I said, green means green. That's not a good definition, right? So what's another way of saying that? F of n can be defined as f of 0 equals 1. So f of n equals 1 if n equals 0. Otherwise, it equals n times f of n minus 1 if n greater than or equal to 0, like that. So that's one way of defining it. So if I use that definition, what would f of 0 be? Correct. What would f of 1 be? So don't tell me the final answer, just tell me according to the definition of the function what it would be. It'd be f of 1, because you're using this definition, right? F of 1 would be 1 times f of 1 minus 1, right? Because f of n would equal n times f of n minus 1, which would be 1 times f of 1 minus 1, which would be 1 times f of 0. But what is f of 0, though? We already calculated that. That's 1. That's 1 times 1. What's 1 times 1? 1 as well. Now what's f of 2? F of 2 would equal what? Which of these two formulas would we use? The top formula or the bottom formula? Right, because we're plugging in n of 2, which is bigger than or equal to 0. So n of 2 would equal n times f of n minus 1. So it would equal, what is 2 minus 1? So it would equal 2 times f of 1. And f of 1 is equal to 1 times f of 1 minus, no, sorry. I did it backwards, my fault. F of 1 is equal to what? F of 1 is equal to f of 1 minus 1. So that's 2 times 1 times f of 0, which is equal to 2 times 1 times 1, which is 2. And now obviously you can see it takes more steps to evaluate a function recursively than if you have it as what they call defined iteratively. So if you define the function in factorial like this, like from 1 through n or whatever multiplied together, this takes less steps because this is just linear thinking basically. But sometimes linear thinking can't be defined properly without using nonlinear thinking. And by the way, when a computer does recursive functions, this is what they call adding something to the stack. So when the computer is in the middle of calculating something, it runs into a sub-calculation. Like it's calculating this formula and then it runs into another function. Then it has to go and calculate that as a sub-step of that first process. That's called adding to the stack. So have you ever heard of like Stack Overflow? That's a website, by the way, but there's something called Stack Overflow. It's when before they had the website, it was meaning that you ran out of stack space. So your function only has your computer only has a certain number of nested steps that it can actually do. And one of the important things in computer science, this is not always possible, but one of the important things in computer science is to try to take something that has a recursive structure like this, try to find a way to write it as a linear or an iterative structure instead. Because that makes it it's a lot less stack space and a lot faster speed in general. Sometimes things actually work better if they're done recursively, but a lot of times, probably most of the time, they work more slowly. If you calculate something in a recursive way, a lot of times it goes slower than if you can do it in a linear way. But there doesn't always exist a way to do something linearly, though. Okay, let's look at one more Ackermann function value because I want to make sure that more people are participating. So has everybody answered one of those questions so far? Like one of the values of something? Okay, I'm gonna go through the list of people and we're gonna do one more Ackermann function. I'll try to make sure everybody answers at least one small question. So make sure you're paying really close attention. Let's go back to the Ackermann function right here. So make sure you're looking at that closely. And I'm going to erase all the bottom part. And I'm going to, so the last one I did was A of 1, 2, right? I'm going to change that to be A of 1, 3. Let's find A of 1, 3. I'm going to keep the A of 1, 2, though. Or well, actually, maybe I shouldn't keep the A of 1, 2. Yeah, I'm going to erase the A of 1, 2 because that'd make it too easy. Okay, so the first person I'm gonna ask a question to is Amani. So just be ready. Okay, ready? So A of 1, 2, right? Or did I say A of 1? Did I say 1, 3 actually, right? So let's find A of 1, 3. We need to find A of 1, 3. So first of all, which letter is M, Amani? The 1 or the 3? Correct. M is 1. Okay, now let me go to the next person. M is 1. And LaShawn, what is 1 minus 1? Correct. And then okay, and then the third person, Anthony. M is 1, right? It comes to M again. So what is M? 1, correct. And then Zoe, it comes to N minus 1. So which number is N? 3. Okay, then it goes to Isaac. Isaac, what is N minus 1? What is 3 minus 1? 2, correct. So does everybody see how I got the first step done? Right? We got the first step by doing M minus 1, then by doing M, and then by doing N minus 1. And we got that from the last line of the formula. Okay, then after Isaac is Anthony. Okay, so we're going to write down the next step. The 0 doesn't matter, that's just already solved. We need to do A of 1, 2. So first of all, which of those numbers is M, the 1 or the 2, Anthony? 1, right? So you're right. So M is 1, and then Colin's not here, but Ignacio, are you here? How about Caleb? Caleb, which of those numbers is N? 2, correct. So the definition says that that Ackermann value of 1, 2 is equal to the Ackermann value of M minus 1, 1 minus 1, and then the Ackermann value of M, which is 1, and then the Ackermann value of N minus 1, right? 1, 2, 3, there we go. Okay, so we got that. Now, next person is gone, actually. Okay, Taylor, what's 1 minus 1? Correct. And then Logan, what's 2 minus 1? Correct. Okay, perfect. So that's what we got so far. Now, last but not least, Mercada. Which of those numbers is M, the 1 or the 1? 1 is, right? Okay, so that one's M. Yep, that's M. And then which one of those is N? Amani, which one of those is N? The 1 or the 1? Yes, correct. Okay, now this one's a little bit harder, okay? LaShawn. Is 1 bigger than or equal to 1? Is 1 bigger than or equal to 1? Think again. Yeah, yes, it is. Yes, so it is. Yes, it is bigger than or equal to 1. And now the next person is Anthony's not here. Zoe. Is 1 equal to 1? Yes. So since M is bigger than or equal to 1, and since N equals 1, which of those cases applies? Third one. So A of 1, 1, I didn't even need to write that down. A of 1, 1 applies to the third value, right? What's the third value equal to? 2. So A of 1, 1 is equal to the third value, which is 2. So we did that. Perfect. So we reduced A of 1, 1 to 2. Now we're going to go back again. So look at those numbers 0 and 2. So who's next after Zoe? Isaac. Isaac. Which of those numbers is M, the 0 or the 2? 0. Correct. And then Anthony, which of those numbers is N, the 0 or the 2? Correct. And then Caleb, is M equal to 0? Yeah. Correct. So which of those formulas is going to apply? Taylor's gone now, but Logan, which of those formulas will apply if M equals 0? 2 in, right? Correct. So this equals the A of 0, 2 equals A of 0, 2 in, right? Except what did I just say the value of n was? What is the value of n? For who's next? Who just went? Caleb? Or no, you are Logan? Okay, Mercada. What's the value of n right now? 2, correct. So this is going to equal 0 and 2 times 2. And then Amani, what's 2 times 2? Correct. And then which case applies if you have, okay, so let me keep going. What's the value of m in this case, LaShawn? If you have 0 and 4, which one is m? Like M&Ms? Sure. Correct. And then Zoe, which one's n? Okay, perfect. And then Isaac, which is m equal to 0? So if m equals 0, Anthony, if m equals 0, which of the lines applied? The top line or the bottom line or one of the other lines? Top line, right. So what's the top line equal to, Caleb? 2 in, right? Okay, then if I plug in Logan, what's the value of n again? Value of n. Yeah. The value of n is still what? It's still equal to the what is that number right here? 4. Yep. Okay, and then Mercado, what's 2 times 4? Correct. So the answer is 8. Is that pretty cool? Maybe it wasn't cool, but this is just basically this function basically helps you practice just to see if you can figure out the details and really understand. Yes.
Did you put another case in there that if m equals 1, then the value is n, like 2 to the n? You know,
Well, you could try. I'll let you experiment with that and figure that out.
Okay.
You could try that out and see if that would be worked. No, I did notice that as well, that we got like 4 and then we got 8.
Yeah.
But I'm not sure for sure because this is complicated, but you can try it though.
Is there any like use for this function?
This is actually an important function. You read the book, you would have known what the use is. It says has an important role in the theory of recursive functions and the study of complexity of algorithms involving set unions. So basically, this function probably has some strange meanings, like in terms of like the unions of sets, and it helps calculate things for the unions of sets. But it's also a great function to practice with. So every time I teach discrete math, always, in fact, probably any good discrete math teacher should always have their students practice with this function, because it helps you understand with very basic numbers how to do things recursively. Okay, perfect. Okay, good job. All right, well, let's stop with that point in terms of chapter 5. Let's skip ahead a little bit into counting problems. So we'll go ahead into chapter 6. Gonna start out basic though, but then it's gonna get kind of complicated though. So we're gonna start with things like you have 3 letters times 4 letters. That's like how many letters you have, which is easy, of course. But then eventually we're gonna get things called generating functions and some other things that they should be just as easy to understand, but if you're not paying attention the whole time, you're gonna go lost, right? Just like, for example, if you're driving down the highway, what would happen if you close your eyes for 20 seconds? Do you want to try it? Who'd be willing to drive down the highway and close your eyes for just 20 seconds? It would not work. It's the same way in fact, really, it's the same way in anything that you're learning. You should never just get distracted even for 20 seconds. Okay, so the product rule is going to seem so basic. In fact, well, I'll go ahead and tell it to you, but then we're going to go a little bit more complicated than that though. So if you have a procedure or an algorithm or something like that, it can be broken down into 2 tasks. So how many ways can a procedure Oh, whoops, I always get my letters mixed up. Procedure be done if consists of two tasks. You would say two, you could actually call it two sub procedures if you wanted to, but if it consists of two tasks, and there are N1 ways of doing the first task. The first task. And there's N2 ways of doing the second task. The second task. So what's the answer? How many ways can a procedure be done if it consists of two tasks? There are N1 ways of doing the first task and N2 ways of doing the second task. Correct. N1 times N2 is how many ways it can be done. We can generalize the product rule to an unlimited number of steps, and by what would we do to figure out how many ways something can be done? It consists of three tasks, and there's in one way of doing the first task, and in two ways of doing the second one, and in three ways of doing the third one. So generalization is that if you have, it'd be N1 times N2 times N3 times N4, dot, 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 however many steps you had, right? So how many ways are there of making a Wendy's hamburger? How many tasks are involved in making a Wendy's hamburger? So what's the checklist for making a Wendy's hamburger? Wendy's hamburger procedure. Let's just keep it somewhat simple. So there might be like a conveyor belt or an assembly line. What's the first thing you'd maybe have on the assembly line for your hamburger? What do you have to start with? The bun, right? So there's like the bun section, and some people might want protein style hamburgers, right? So there's actually how many options for the bun? They could have maybe a sesame seed bun, maybe like a regular bun, maybe no bun. So maybe they could even have 4 different kinds of buns. So I'll let you decide how many kinds of buns should they have, including no bun. 3. So let's say 3 different options for the bun, and then they go to, let's say, the cheese section. How many options do you think there are for the cheese, including no cheese? 4 options, okay. How many options are there for the hamburgers? Maybe like no hamburger, which would be weird. Hamburger with no hamburger. What would that be? Like a vegetarian style hamburger? You can maybe have like a Beyond Meat one. You could have like one, or you have like 1 patty or 2 patties. Like how many options do you think there could be? 6, okay. So 6 options. And then you have like the pickles section. People might want pickles or no pickles or lots of pickles. So let's say that there's 3 options for pickles. This is already getting tiresome. What do you think the next section is? Well, let's say what's something that there's only 1 option for, either yes or no? Ketchup, okay. I guess I'll go with that, although you could have extra ketchup though. But that's fine, though. We'll just say 2 options for that. Because who would want just a little bit of ketchup, but maybe some people would. Well, let's do like 2 more toppings. What are a couple other toppings you could have on your hamburger? Lettuce. Okay, that would be like a yes or no, right? Although you could do extra lettuce, but so 2 options for that. What's the option at the cafeteria that everybody likes on their hamburgers that they never let you have? Well, they sometimes do. They don't. Bacon. Bacon. Oh, eggs too. Yeah. So bacon, we could say there are 2 options for that. And eggs, 2 options for that. Yes, egg or no egg. Although you could do like over easy egg, over hard egg. Like you could really have maybe 3 options for eggs actually. So let's stop there because we could go forever. If those are the steps on the conveyor belt, the buns, the cheese, the burgers, the pickles, the ketchup, the lettuce, the bacon, and the egg section. Okay, how many total ways are there to make your hamburger? Well, you got to do 3 times 4 times 6 times 3 times 2 times 2 times 2 times 3. So how many would that be? Well, I'm gonna do them 2 at a time in my head, like 3 times 4 is 12. 12 times 18 would be the next 2, times 2 times 2, that's 4, times, and then 2 times 3, that's 6. So if I do half of it in my head and half of it on the calculator, it's 12 times 18 times 4 times 6, 5,184 hamburgers. So have you ever heard the ads where there's a restaurant that says, we offer 500 or like 5,000 kinds of hamburgers? That's what they mean really, is that they have like, if you did all the different options that you could possibly get, it would add up to like 5,000 different options. So they really don't make 5,000 different hamburgers because they're really the same kind of burgers, maybe, or well, maybe 2 options really, but if you think of all the different ways that you could have them though, then it'd be 5,000. So if you're really crazy, you could go to Wendy's for every day for the next 15 years and try to have a hamburger every possible way. That'd be sort of silly. So you now know the counting rule. Now I'm going to teach you one more thing today that's probably a lot more important than even that. This is how many unique ways to use symbols to make something. So making a unique thing, I'll just say thing, from pieces. I could say string. They do use the word string sometimes, and I'll just say thing because I don't want to make it too complicated. Making a unique thing from symbols. I'll just say symbols. But I'm just going to say letters / numbers. So it could be other symbols too, but I'm just going to keep it simple and use letters / numbers. So we're going to start with the word Mississippi. Missississippi, right? Did anybody ever have to learn to spell the word Mississippi when you were kids? So has double S's, double P's, and I's in between everything. So Mississippi, how many unique things or how many unique things from those symbols? From those symbols. You have to use them all. So that's assumed you just have to use all the symbols. You could if you wanted to. So I'll give you a hint. First of all, count how many letters there are or how many symbols there are in the thing. How many symbols are there within that thing? 11. So you put the number of symbols factorial. Let me change the n to be the number symbol because n could be a specific variable. So the number of symbols that you have factorial. So I'm going to do what you said and use this word factorial, the symbol factorial. Divide. So why would you do that? Because every time, let's just hypothetically say that you have 5 symbols to use. How many choices do you have for the first symbol to put at the beginning of the thing that you're making? You would have 5 choices for the first one, right? Or in this case, we have 11 things. So we could use any of those 11 letters to put first, right? But then once we put it first, though, anytime you put something down, even though you have a free choice of which one to put down, once you've already put it down, you can't use that letter anymore. So then you have only 10 left. You have 10 options for the next one. So this is like making a hamburger where you have 11 choices for the first stage of the conveyor belt. Then you have 10 choices for the next stage, and then you have 9 for the next stage. So that'd be 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which is another name of which is just the same as saying 11 factorial, right? But there's a problem with that though, Because how many letters S do I have? So if I move this letter S and switch it with that letter S, is that a different result? No, that's the same thing, because S is the same as S. So every time you permute or exchange one of the same letters with itself, you have not made a unique thing anymore. So how many S's are there?
4.
Yep. So you have to take the number of duplicate symbols, factorial, dot, 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 times every other number of duplicate symbols, factorial, for every different duplicate symbol. You've already learned this in college algebra, but probably. So there's 11 symbols total. And how many duplicate symbols are there? How many different kinds of duplicate symbols are there? Is there a duplicate M? No. Is there a duplicate I?
Yeah.
Yes. So we have to put, how many duplicate I's are there?
4.
So we have to put 4 factorial on the bottom. How many duplicate S's are there?
4.
How many duplicate P's are there?
Oh.
Yeah, so it's 11 factorial over 4 factorial times 4 factorial times 2 factorial. And then that's too big to calculate in our head, probably. You could always go to Google the Great. Let's calculate that on Google the Great. So it's going to be, let me just search for hello first to bring it up bigger. There we go. So 11 factorial divided by 4 factorial times 4 factorial times 2 factorial. That equals 34,650 different things you can make from the letters in Mississippi that are always different from each other. So that's the end of today, but we're going to be learning other counting rules and procedures continuing on in chapter 6 after this as well. And remember, some of you missed this because you weren't here on time, but you're going to be able to take your test, meet with me during my office hours. Has to be during my office hours. If you have something else going on, you need to try to work around that somehow. You'll be able to get half credit on any and everything that you didn't get perfectly right by going over with me and learning how to do it in my office hours. And I can't force you to do it, but I want you all to do it for everything you missed, because even if you skip 3 questions, not a single question on this test, it was unimportant. You still need to learn that to help meet the outcomes of the class. Out of the whole first 8 weeks, I didn't even have very many questions that I actually tested you about. So all of them are important. So if you didn't get your test back yet, let me go hand it back to you right now.